Hey everyone. All right, we're back at it here with grade 12 University Physics, here with Mr. Stone. So we're looking at now what actually happens now that we've defined these laws of special relativity, right? The postulates, but basically that in every inertial frame of reference, the speed of light is constant. What does that do for our understanding of physics, causality, and everything? Basically, it changes all of our viewpoints. So, um, what have we done so far? So, if we apply the postulates of Einstein's special relativity, then what it really means is that space and time are kind of the same thing. They're all part of a four-dimensional framework, which we're going to call SpaceTime. And the links is a little bit complicated, right? Um, the link between time and space depends on velocity, right? Uh, the time sort of gets mixed up with the spatial dimension when we start traveling close to the speed of light. Namely, a time interval is not absolute and depends on the frame of reference in which it's measured, the velocity of that frame of reference. Right? If you're inside the frame of reference, then the frame is, we call it, at rest. But if you're outside of the frame and is traveling at a velocity v, the time that takes place, the time interval that's happening, the rate in which time flows in that frame of reference is slowed down. And we're able to switch between those frames of reference. And we can do that. Before, we use something called a Galilean transformation, where we just add and subtract velocity. But it gets a bit more complicated with space-time, and we have to use what we call a Lorentz transformation. And that's what I've gotten down here. This is beyond our course here, but this is the Lorentz transformations, and you can see that it's almost the same here. So delta t is, this is this gamma t, but then there's this other guy here, this correction term, which we're really not going to worry about too much. Okay, but what I'm interested in is thinking about a rocket ship as it's traveling from Earth to some distant star, and it's traveling at a speed v. Now there's two observers. One's on Earth, and there's one on the spaceship. So the rocket ship captain, he's inside of his spaceship. So he thinks of himself as at rest. So what he sees is the Earth moving away from him, behind him, and the star coming towards him. So he sees space moving at the speed v by them. Okay, so they're at rest and they see space moving. Just like if you're inside a car, it looks as though the road is moving past you, or things are moving past you. But from the frame of reference of those objects, you look like you're going in the opposite direction. Okay, so from the inside of that spacecraft, you'll see himself traveling some time interval delta t. Okay, that's the time that the spaceship captain takes to get from Earth to the star. So the distance that they measure in that frame of reference will be the speed at which they travel times that time interval. So v delta t will be the distance that the captain of the spaceship observes. That's the distance between Earth and the star. Now, us on Earth, we will see the rocket moving away from us. It'll be a moving frame of reference. And that means that moving frame of reference will have its own slower time in using the notation from the last lesson, which we'll call DeltaT Prime. So that DeltaT Prime multiplied by the speed at which they're traveling, right? Remember, that's a slower time. So they're going to think that they're taking less time inside the spaceship, but we're going to see them as having taken more time. So that delta t is going to be larger, right, using what we learned last lesson. So delta t prime times the speed at which they take, right, that we know that's their speed traveling. That's going to be the L that we see. And we know that there's this time dilation happening. This is the expression that we derived last lesson, that the time inside the moving frame of reference, when viewed from the outside rest frame, will be the rest time inside divided by this term, this gamma term, or multiplied by the gamma term, sorry. So what that's going to mean, right, if I rearrange these equations, is that the distance measured in an inertial frame in which the object is moving is smaller. We will see the rocket ship looking smaller. Inside the rocket ship, it'll look as though the distance shrunk between the planet, the Earth, and the distant star. They're going to see that distance shrink. Because they're traveling so fast, they're going to see the distance actually small. The ruler between the two, the star and the planet, will actually get smaller for them. For us, we will see the spaceship contract. The people inside the spaceship won't see any change. They'll see the world outside contract. We from the outside will see the spaceship contract. This is mind-boggling. So really, if I'm watching the Starship Enterprise fly by me, at 0.99c, I will not see the rest frame Starship Enterprise. I will see this contracted, this squished one. That doesn't mean that the people inside of here see that their hallways have gotten smaller, their rooms have gotten smaller, because they themselves have gotten smaller. So all the meter sticks, everything that you use to measure, every idea of length has contracted inside the starship, and they won't see that at all. What they will see is that the universe outside of the starship has contracted, because every frame of reference has to be correct. There is no absolute frame of reference. I will be observing a spaceship go by me, so that it'll look like it's compressed. From the inside, it'll look as though the Earth is going in the opposite direction. So it'll look like the Earth is squished. So instead of the Earth being a sphere, it'll be squished down to an oval in the direction of travel. Both are correct, because the speed of light has to be the same in every inertial frame of reference. We call this length contraction. So let's do a quick example here. Let's say I have a 100-meter rocket ship, and it's passing by a 10-kilometer wide space station. The rocket ship is traveling at 95% of the speed of light. But what is the width of the spaceship measured by a viewer on the space station? And what's the width of the space station measured by a viewer on the spaceship? So, from the point of view of the space station, the spaceship, once I plug this in, it'll squish from a 10-kilometer view, the width of the spaceship. 1 second, I got this backwards. So, the 100-meter spaceship is going to be squished down to a 31-meter spaceship. Words. Okay, and from the other point of view, from the spaceship, the space station will have squished to a 3.1 kilometer space. Okay? Even though from the viewpoint of the space station, they're going to see no change. They will see a smaller spaceship go by, but from the spaceship, you'll see a smaller space station go in the opposite direction. And this has to happen for the speed of light to be constant in both frames of reference. Mind-boggling stuff. All right, let's go even farther. Okay, so because we're compressing space in the direction of motion, this has some very strange effects on light, because light traveling at the speed of light, c, has to travel at the speed of light everywhere it goes. But if a source is moving at some speed less than the speed of light, but close to the speed of light, that's going to be catching up to its light. It's going to be squishing the light waves together. So in the same way as when we had waves in air or waves in something, we caught up to them with something called the Doppler effect. Right? When a train goes by you, right, it's a higher pitch as it's coming towards you and lower pitch as it's going away from you. In the same way, light is shifted. The frequency of light changes with respect to its motion. So let's say we have some light source, and it's traveling towards us at a speed v. When considered at rest, we can say that the wavelength of light is the distance between successive crests or wave fronts. Okay, so this is the wave front here. This is from the rest frame, the object that the source of light here is going to produce waves in the electromagnetic spectrum. And those wavelengths are just going to be the speed of light times the period. Okay, where the period is the period of the electromagnetic radiation that's coming out of it. Okay, and we're going to call that T, and that's the rest frame time. You can see where we're going with this. Now, if it's moving towards us, that rest frame time is no longer. We're going to have to apply a new time, right? A new interval instead of the period of going up and down. It's going to be now delta. It's going to be T prime, which is our time dilated version. And not only that, is we're going to have to not only have the speed of light which is traveling, but we're also going to have to get rid of or subtract here the rate in which it's traveling towards us. Right? We're going to have to subtract v delta t because it's going to be traveling towards us at some speed v. Right? These waves are going to be traveling towards us at a speed c. The source itself is going to be catching up to those waves. Okay? So from our new viewpoint, the distance between successive wave fronts in terms of the time measured between the creation of wave fronts, delta t prime, because we're measuring this from the outside perspective here, from this guy. He's at rest, the source is now moving, so it's going to be time dilated. I'm not going to go through the full proof, it's a little bit too complicated for us here. But we actually have an expression for the new observed frequency of light. So if a light is approaching us, the frequency actually ends up being what we call blue shift. The wavelengths the waves are gonna get squished smaller and smaller and smaller. The light is gonna appear to be at a higher frequency. It's gonna be shifted towards the blue color, right? Because blue has higher frequency. The red, we call this a blue shift. Okay, so anytime that a light source is coming towards us, we'll actually see it's looking bluer than it's supposed to. And if it's going away from us, it'll look as though it's going in a redder light than it should be. Right? Since this coefficient has to be greater than 0, since this term here is going to be larger than the term below, this whole term is going to be larger than 1. So the observed wavelength will be larger than the actual wavelength that it is. So it's going to be called redshift. Okay? And what this does is does some very strange things to how you would see the universe going by you from the point of view of, let's say you have a window inside your spaceship. Notice what's happening here in the rest frame, this black line is something that would be at 90 degrees to you. But once you're traveling close to the speed of light, it's actually in front of you. And objects that were behind you, see if I can keep track of one of these things, is actually in front of you again. So everything behind you is actually going to become in front. You're going to see all the stars and everything around that you're traveling through. That view is actually going to be squished towards your front, and it's going to be blue shifted. Okay, all those things are going to actually be blue shifted in front of you, and all the things that were behind you is actually going to be to the side, and are going to be red shifted. And if you travel at the speed of light, there'll be nothing behind. Not almost, like 99.999. There'll be nothing behind you. It'll be black behind you. Everything that's in that 180 degrees around you is all going to be in front of you in this rainbow pattern. Okay, and that's what this is showing here, because this is showing what happens to time and space here. Basically, our typical normal Cartesian coordinate system is all messed up. It's all convoluted here by time. That time dilation changes the way the metric, we call it, of space time. Okay? It's awesome. Anyways, another thing that this tells us is because we know wavelengths of certain things, like hydrogen, for example. Hydrogen is the most common element in the universe. 75% of the entire universe is made up of hydrogen, right? Because it's so simple. It's just one proton, one electron going around. Stars are almost entirely made up of hydrogen, right? And stars give off that light from excited hydrogen. And we'll be seeing later in this unit what these frequencies are. But one of the frequencies, or wavelengths, right, is a line called 656 nanometers, or the hydrogen alpha line. Right, and in the rest frame, that's what we measure hydrogen to excite at. We can see this is the spectrum in which hydrogen has these 5 lines, which we call the Balmer lines. And there's this one here, which is 656 nanometer. And we know that hydrogen produces that light. We're going to take a galaxy that's 4 billion light years away. Okay, so it's 4 billion years in the past. It took 4 billion years for that light to get to us. But the light, this spectrum here that should be in this position, everything has been shifted into the reds. So much so that the red that we would expect, the 656, is actually into the infrared. Can't actually see it with our with our eyes. It's 800 nanometers. And if that's the case, how fast is the galaxy moving? This is one of the big discoveries of the 20th century, is that every distant object in the universe is redshifted. What does that mean? What does that mean that all objects in the universe are actually going away from us? It was the first real evidence we had of our expanding universe, the fact that the universe is getting bigger all the time. The Big Bang happened because we know that as time goes forward, everything is getting bigger, which means that as we go backwards in time, everything has to get smaller and smaller until it's compressed down to a little point. This was our one of our first pieces of evidence the Big Bang existed. Right? So this is not saying that this galaxy has some sort of rocket that's pushing it away from us at some speed. This is that galaxy is the space, the actual fabric of space-time between us and that galaxy is getting larger. The whole fabric of reality is expanding. The universe is just getting larger, and it's not that it's the space in between really is getting larger. These are some big ideas, but that's really what we're seeing. And we see this in this Doppler shift of the hydrogen line, this 656, being pushed out to 803. And what does that mean? Let's plug this into our formula here. And we're going to rearrange, multiply both sides by the denominator, square everything, multiply by C, top and bottom in both of those fractions. Then we can cancel things out. We'll multiply. We can expand. We're going to expand here. We're going to expand here, and the C below will cancel. We end up with this expression. Let's put all the, what did I do here? I just rearranged, and I come up with an expression for the speed of the source relative to the two wavelengths, the observed and the source wavelength. Now, if I plug those in, I end up with 20% of the speed of light. So a galaxy that's 4 billion light years away from us is actually is going away from us at 20% of the speed of light. Ridiculously high number. Okay? And that's because the universe itself is expanding. And not only that, it's accelerating, but that's a different story altogether. We'll leave that for today. Okay? So what have we done here? We multiplied both sides by the radical, squared everything, multiplied by C on both sides, and then we brought all the V's over to one side, all the C's over to one side, rearranged, and we got our final answer. Okay? A frightening realization for physicists in the 20th century when they realized that the galaxy is, not the galaxy, the universe is expanding at a tremendous rate. So yeah, the galaxy is traveling away from us at 20% of the speed of light. All right, So what I'd like you to do is, there's a couple of homework problems. This is about length contraction, these 6, 7, 8. And then there's a problem here about this redshift. Now, when we measure redshift, astronomers typically use a number called Z, which is what they use to as a sort of a fractional redshift, which is the actual frequency that's emitted subtracted what we observe. So this would be like 656. Take away the frequency observed and divided by the frequency observed. So 656 take away 803 divided by 803. Okay. And that gives us what we call our redshift. This is letter Z. Now, the most distant object that's ever been observed by human telescopes is something called GN-Z11. Z11 is because it's redshifted 11.09. What does that mean in terms of its velocity? How far away is it traveling from us? And what would be the observed wavelength of the hydrogen alpha line? Okay, so that's for you guys to work on. All right, so again, these are some big ideas and some big scary things about, the universe is not an absolute, lengths are not absolute, times are not absolute, frequencies are not absolute. There is no absolute frame of reference. Everything is related to how we're measuring it. Okay, so maybe you guys can think about some of these big ideas. All right, take care.